So I'm Brad Chamberlain. I'm a distinguished technologist at Hewlett-Packard Enterprise. The last few talks I've given at this workshop have been focused on kind of latest and greatest technical hits that our group has accomplished. And this one's going to be kind of different. I'm going to give you an abridged version of a keynote I gave last summer. This was at a workshop called HIPS, which is about high-level parallel programming models. And it was the 30th instance of the HIPS workshop. So I took it as an opportunity to look back on the past 30 years of scalable parallel programming. And to kind of tip my hand a little bit, the takeaway is we've had so many hardware advances and yet so few broadly adopted programming languages. So a couple of terms I'm going to use in this talk. HPC for me means high performance computing, or supercomputing if you will. You may not be interested in HPC or supercomputing, but you may be interested in many core programming or GPU programming or the cloud or AI data centers. And I think there's a lot of commonality between those and HPC. The other term I'm going to use is locality control. To me, this means the ability to control and or reason about the placement of data and tasks. So things like allocate this variable in this memory or maybe in this other memory, run this task here on my processors or maybe over on your processors or maybe wherever that data was allocated. So those are two terms I'm going to use today. Now, like any good talk reflecting on N years of HPC, I'm going to turn to the top 500. If you're not familiar with it, this is a website that tracks the top 500 ostensibly most powerful computers in the world as measured by LinPack benchmark. And I'm going to look at just the top 5 30 years ago versus today. If we look at the top 5 30 years ago, I've got here the core counts, the Rmax value, which is essentially the performance that it achieved. Here it's measured in gigaflops, the systems and the network topologies that were used in these top 5 systems. And if we look at the most recent list, which came out this past November, we see a lot more cores, a lot more Rmax. It's now measured in petaflops, right? So the number of cores has increased by hundreds to hundreds of thousands, and the Rmax value by millions to tens of millions. This is a massive, massive increase in power. And HPC hardware, as a result, has become far, far more capable. And if we look at the reasons for this increase, there are a bunch of them. Commodity vector processors have come online, commodity multi-core and many-core processors. We have multi-socket compute nodes. All of these things lead to NUMA processor and node architectures. We've introduced high-radix, low-diameter networks, and GPU computing has really come to the fore. Something I want to note, though, from a programming perspective is that all of these changes have made the system much more complex, and most of them, I would say, have made the systems much harder to program. The only one I think that has arguably a benefit from programmability standpoint is the high-radix, low-diameter networks. All the rest are kind of imposing more challenges on the programmer. All right, so let's turn now from hardware to looking at software over that same time period. If I reflect on what were the broadly adopted notations used to program HPCs in, again, 30 years ago, the languages we were using were Fortran, C, and C++. When you had internode concerns, we used these communication libraries, MPI, PVM, and SHMEM. Within a node, we would use pthreads or vendor-specific pragmas. And before I made this talk, if you had asked me, I would have said, in OpenMP, of course. It turns out that didn't come along until a couple years later, but it's been around for most of the past 30 years. And then various scripting technologies. Now, if we look at things today, it really hasn't changed so much. To color code that for you, the biggest change here is the introduction of GPUs. And with them, there have been a number of new notations added because, frankly, our previous notations just weren't up to the task of being able to program GPUs well. A couple minor changes in intranode programming, a couple minor changes in scripting, or actually, I guess more major changes, I would say, in scripting for the good. But generally speaking, our HPC software notations have largely stayed the same, modulo the introduction, again, of GPU programming and the scripting benefits. And I would say most notably, HPC has failed to broadly adopt any new programming languages, right? At the core here are still Fortran, C, and C++. And so it feels like while hardware has made these massive advances, the HPC programming technologies have more or less stayed the same, and maybe even lost ground because of the increased hardware complexity that I mentioned before. And yeah, I was just noticing that. All right. So a question we might ask. So why is HPC so stuck? Why have we not broadly adopted any new programming languages? And I'm going to offer up some straw person arguments and then kind of knock them down. Some people might think maybe it's because language design is dead, right? Maybe we have all the languages we need. Reflecting on my own life 30 years ago, I had just, with my team here at UW, submitted one of our first papers that was rejected with a reviewer saying, you know, programming language design ceased to be relevant in the 80s. And it was like, really? And of course, that seems very unlikely. If you look at all of the languages that have either been developed or risen to prominence in those last 30 years, there are a lot of them, and these aren't just kind of esoteric academic languages, right? These are languages that have become favorite day-to-day languages for a lot of people across multiple disciplines. That said, they're not really HPC appropriate or ready necessarily, primarily because of the lack of this locality control I mentioned before, saying where things should run and where things should be allocated. Now, if we look at what caused these languages to rise to prominence, I think there are 4 main factors that they tend to focus on or that cause them to catch on, which are productivity, safety, portability, and performance. And I really like these because these are 4 themes that I think are really, really important in HPC as well, where I would argue that productivity and safety are the ones that traditionally we've paid the least attention to. All right, so another possible reason for not having new languages, maybe we don't need new languages. Maybe Fortran, C, and C++ are optimal somehow. It's certainly true that they are sufficient, and I would say using them in combination with libraries and directives and extensions has gotten us really, really far. If you look at almost any major HPC result from the past 30 years, it was developed using these technologies. But at the same time, using C++ with MPI, plus maybe OpenMP or CUDA, leaves a lot to be desired from a productivity standpoint. I think most of you, if you started using these, if you don't already, would feel like I threw you into a time machine and sent you back, decades and decades. They're not very safe, and because they're sort of serial language and library based, you don't get very many automated optimizations. So I tend to think that we in HPC are living in a state very similar to when Fortran was first introduced to assembly level programmers. We are accustomed to moving data around the memory hierarchy manually. It's a different level of the memory hierarchy than assembly programmers would have used, but we're doing everything very explicitly. We're very skeptical about higher level approaches, and we're hesitant to give up the control and the performance that we have or that we think we have. And I think as a community, we really undervalue the benefits of things like readability and maintainability of code, safety, compiler checks, and optimizations. Things that, again, I think hopefully most of you kind of take for granted. So hopefully this is not a controversial statement for this crowd. I think programming languages offer a lot of unique advantages over libraries and extensions, and that's where we need to be going in HPC. So another reason you might think we don't have new languages is maybe we just haven't really tried to tackle this problem. But if you follow the field at all, that's definitely not the case. Many, many, many attempts have been made to create parallel languages and HPC scale languages. I've called out some of my favorites here and kind of sorted them into this loose taxonomy. But the fact of the matter is none of them have been broadly adopted. And to be clear, I don't mean to say that all of these languages are necessarily worthy of broad adoption. Many of them were interesting experiments that didn't pan out or whatever. But a lot of people look at this list and say, like, therefore we just shouldn't even bother trying anymore. Like, look at all these failures. Whereas my attitude is much more like, well, let's learn from these failures and see how we can improve upon them. So as you heard, I'm part of, or no, I guess I didn't say it. I'm part of the Chapel language team at Hewlett-Packard Enterprise. So one of the languages on here that I care about is Chapel. It's still ongoing. So while we haven't been broadly adopted, we haven't fallen over yet either, as many of these have. Let me talk briefly about what Chapel is and how it fits into this 30-year landscape I've been painting. So if you're not familiar with it, it's a scalable parallel programming language. It's open source and collaborative. We do all of our stuff at GitHub. And since the last time I gave a talk here, we've actually joined the Linux Foundation and its High Performance Software Foundation, which is an HPC-oriented open source sub-foundation. In terms of timeline, we conceived of Chapel in 2002. The design got its traction in 2006, and we did our first public release in 2008. So we're about 20 years old, give or take, depending on how you want to count it. All right, so going back to some of my previous slides, talking about the massive hardware changes that have taken place, I think one of the things that's really interesting about Chapel is that it actually predates all of these hardware technology changes I mentioned, with the exception of the commodity vector processors. So those were around, but multi-core wasn't really a thing yet, multi-socket wasn't, NUMA wasn't, and yet, despite all of these changes, we're more or less using the same language that we designed 20 years ago. And the reason for that is that we focus on expressing parallelism and locality independently of the hardware mechanisms that will ultimately implement it. So we say things like, do these things in parallel, do them here, do them there. We don't talk about message passing or kernel launches or things like that. In terms of software notations, Chapel essentially replaces the need to mix multiple notations for different types of parallelism. Instead of using a language and an internode notation, and a GPU notation, we're just going to use Chapel for all of that. And again, the way we can do that is that it's a language that expresses parallelism locality independent of the hardware mechanisms. So the result of this is things I've shown you in past instances of this workshop. I've pulled up some some slides we've shown over time, and just to pick out this one arbitrarily, we would often show you things where, like on the left here, we've got a reference version of a code written in C++ and MPI and OpenMP. In the middle in blue, we've got the equivalent Chapel code, much more short and succinct. And on the right, we've got performance and show that we're competitive or better. And again, I think this comes about as a result of having this higher level design. Happily, over time, a number of people have been able to apply Chapel to a number of different fields. We've started a series of interviews on our blog where we're interviewing people and asking them about what their work is and how Chapel's helped them and what they'd like to see change. I've got almost a dozen of those up now. So if you're interested in reading about people using Chapel, that would be a place to look. All right, anyway, if you noticed, I never answered my question. So why hasn't HPC broadly adopted any new languages, including Chapel, despite all of its virtues I've just hopefully sold you on? I'm going to say there are a lot of reasons for this, and I'm not going to say they're necessarily good reasons, but here's where we are. I think HPC is a unique community with unique computational needs. That said, I also think there's more and more overlap with mainstream computing through AI data centers, the cloud, things like that. We have to focus on maintaining legacy codes, which are often written in Fortran C, C++, then are writing new ones, and so we get kind of stuck there. I think as a community, our ratio between investing in hardware versus software is way skewed towards hardware. I think software gets short shrift and doesn't get the funding or attention it often needs. As a result of that, whenever we develop a new piece of hardware, we say, well, what do we need to program it? We develop some new notation, and then we kind of stop. And so we end up with this alphabet soup of all these different notations we mix together, rather than creating something unified that sort of takes care of all of them. I think we doubt as a community that we are a large or important enough community to warrant and sustain a language of our own. Though again, I think given the increasing overlaps with mainstream computing, if you will, I think that's sort of a false thing we shouldn't get trapped in. I think we don't have good frameworks within our community for sustaining HPC software once it gets past a research stage. Like, it's not hard to get research funding for HPC software, but then once you've made it, even if you're as prominent as MPI, it's really hard to get a sustained budget. Finally, independent of HPC, we've got all the normal social and political challenges of getting a new language adopted, which every language has to go through. So if this were the full keynote, if I had a full hour, I would then talk to you about some things we could do to nurture language adoption in HPC. But I think most of you aren't HPC people necessarily, and so you're not really the people I want to preach to. Let me talk instead about a question that comes up, I think, increasingly frequently for us, which is, now that AIs can program, again, your mileage may vary there, do languages like Chapel that purport to be higher level, easier to use, whatever, do they really matter? Like, if the machine's doing the programming, do we care? I'll say my answer to this is definitely, at least for the foreseeable future. I'd be interested, I think some of you might disagree, and I think that'd be an interesting debate. Part of my answer is that I think if I were an AI, I'm not an AI, if I were an AI targeting, I think I'd rather target a single unified parallel language than this sort of, again, mishmash of all these different notations. It just sort of seems to me like if it's all about translating an idea from one language or semantics into another, sort of targeting a single one rather than this, again, hodgepodge of different notations we have would be more straightforward. But even if I were wrong about that, as long as we're in a world where humans need to check and maintain AI-developed code, you want code that you're going to be able to read and understand. And frankly, that C++, MPI, OpenMP, CUDA world is very, very difficult to understand, I think, for humans, if you're not the one writing it. All right, so wrapping up. Just as a couple of closing statements, I consider current and aspiring scalable parallel programmers to be at least as worthy of modern languages as the Python, the Rust, the Swift, the Julia communities are. And I think it's a shame that over the past 30 years we haven't really broken through on this. And then looking forward, I think over the next 30 years, I really hope to see the number of broadly adopted languages for scalable parallelism grow to be at least one rather than the current number of 0. For a little bit more information about any of these things that may have intrigued you today, if you like hearing me wrestle with these kind of socio-technical things, there's a blog version of this talk that goes into a bit more detail than I had time for today. And then if you really like my writing, there's a very long series that kind of takes a bunch of things that people use as arguments against new scalable parallel programming languages and sort of rebuts them from my perspective. If you want to know more about Chapel, there's a ton of resources out there. But the main one I wanted to plug is we're going to give a talk at the Northwest C++ users group in a couple of weeks and a demo. We invite you to join us. That'll be a little bit more introductory. That's held over in Bellevue or virtually. If you're interested in those applications of Chapel I popped past, again, this 7 questions for Chapel users interview series is what you want to look at. And the last thing here, if you want to know what's keeping me up at night, like a lot of open source R&D in the current climate and situation, we're actually in a position where for the first time we don't know how we'll be funded after the next 6 months. And so we're trying to figure out what is our path forward, other collaborations we should be doing, new sources we should tap, or have we lost our opportunity to kind of hit it and move on? So with that, I'll turn it over to questions and just put these back up. Thanks.
Thanks. Who have we got with a question here? I'll run over to Gus and then run a second mic. So if you have a question, please raise your hand and I'll get you the second mic.
Thanks for the talk, Brad. I was surprised to not see like the, I guess, portability as a main problem in a unified adoption of like a single HPC. Is it not the case that like every machine, I imagine every big machine has plenty of thorns when you want to run like a program between these machines? You might need to completely refactor your code or change a bunch of parameters at the very least. Is that not? I'm not an HPC person. Yeah. Is that not the case?
No, I mean portability is definitely an issue. I think that one of the ways we deal with portability. So we have some layers that are very portable, like MPI is a good example. Like there are a bunch of different networks, they have different favorite ways of talking to them. MPI sort of creates a common API for programmers to target either directly or through libraries. The other thing we see in portability is things like, a bunch of different GPUs coming out, each of which has its own favorite dialect, whether it's CUDA or HIP or SYCL or whatever. And there are obviously attempts to try to create portable GPU layers, but few people are going even higher to sort of something that's portable across GPUs and CPUs and the next generation of accelerators or things like that. For a language like Chapel, portability is definitely an issue from an engineering perspective in the sense that it comes up in things like code generation, comes up for things like, again, talking to the network, or how do we target all these different GPUs. I think fortunately what we're finding is even though the community is invested primarily in these lower level technologies, they've also invested pretty well in open source technologies. So like using LLVM as a backend compiler for either CPUs or GPUs takes a lot of the sting of sort of processor portability out of it. And then for like network portability, we don't target MPI, that's a bit higher level than what we would like, but there are other network protocols that are designed to be sort of cross multiple networks. Unfortunately, there are 2 of them rather than 1, which is the number you'd like. I guess my point is, we don't have to worry about every system differently because of other sort of low-level portable layers. But that said, it is a lot of work, right? Like, as an example, Chapel's really good at targeting AMD and NVIDIA GPUs today. There's no reason it couldn't target Apple Silicon or Intel, and yet we just haven't had the time to kind of connect the wires up. But there's a path there. It's just work.
Maybe we can take a question from over here.
I was wondering if these newer concurrent languages have good interop with existing, like the C++ and Fortran legacy code, so that you could rewrite, add on to an existing system and do FFI rather than needing to completely rewrite.
Yeah, that's a good question. So it's definitely the case, I think, for any new language to be interoperable is sort of like necessary. And I think, this really started with Java. I think was one of the first languages to really consider interoperability as like a first-class concern in the design. So for us, that was definitely a part of our design, the ability to call out to C or Fortran or to be called by C or Fortran, and more recently, Python and C++ and things like that. So yeah, I think it's crucial for adoption and also a great way to, as you were saying, bring a new language into an existing code base without having to start over from scratch.
So I've got a question about the sort of the sociology of how these things get funded and get adopted. So things like, Java came out of Sun, C came out of everybody who wanted Unix, and you couldn't do anything with Unix without C. But then something like Rust doesn't seem to have had like a corporate sponsor or a real tie-in. Do you have any sort of feel for what it would take to kind of get some community to exist on this stuff?
It's challenging, and I think some of the challenges to community in HPC beyond just kind of the overarching focus on hardware are you want it to be open source because nobody wants to pay for languages anymore. But then if most of us are working for hardware companies and the hardware companies are like, well, how are we going to use this to sell more hardware? And I think there's a story to be made there, but it's pretty secondary or tertiary as opposed to like people will pay us to write their codes in Chapel or whatever. So I think that is one of the social challenges is as you're saying, a lot of the past languages I think have had companies backing them. Even with Rust, I think there's sort of a Mozilla tie-in, and while we've obviously had the privilege of working for Cray and then HP in developing this language, I would say that both companies, to be quite honest, are very hardware focused and don't really know how to market software.
We have one more question over here, and then maybe we can move to the next talk.
Okay.
Thanks for an interesting talk. So you mentioned that Chapel has remained roughly the same, even though hardware has advanced significantly, right? But there are some hardware features which require programming language extensions or modifications to exploit. And if you don't exploit those features, you're not going to get peak performance on that hardware. For example, Hopper GPUs has this tensor memory accelerators, right?
Right.
And CUDA language itself had to add these things.
That's right.
So what's your take on things like that?
Yeah, so there's always this question along the lines of what I think you're saying, which is, the things I focused on here are primarily CPUs and GPUs, and those have this kind of von Neumann structure to it, right? But what if we get something a little more exotic or a little bit more specialized? Like, how do we deal with that? And I think the further you go along that spectrum, to me, it becomes maybe less a question of how the language targets it and more a question of, like, what libraries do you want to expose through the language to the programmer? So my hope would be that, and to be clear, I'm not saying, like, I have seen every possible hardware future and this will satisfy it, right? But I think as something becomes sort of less general purpose and more specialized, exposing that through language as a library kind of interface rather than as first-class language concepts is probably the right way to go. So that's my short answer to that question.
Okay,
I think I'm out
thanks.
of time, but I'll be around all day.
Let's give Brad another round of applause.